Awesome, it's recording. Alrighty. Cool. So, first thing I want to talk about is the calculations for part D. So something to keep in mind about this step here is that what we are trying to do is we are trying to, now that we know the concentration of lactic acid, to work backwards to figure out, does it match the original claim? So this is the lactic acid. Part C, you found the concentration. And now we're trying to work backwards to check whatever the manufacturer has claimed, or whatever the, what the technician has claimed when they purified it. So if we look back into, I'm just going to grab the stuff from previous. Actually, did I even stay here? Yes. All right, so just as a reminder, when you guys did part A, there was a statement. Let me just grab it from my website just so we can see it. That's B and C, part A. All right. I think that's the one I want. All right, so just as a reminder, part A for the teaching set, we were looking at the analysis of sour cream, and we're trying to figure out the lactic acid in there. So what had happened was that lactic acid is found about 0.55% when you buy in the supermarket. However, it is not very pure at that point, and we have a lot of other stuff in there. So we've given it to the lab technician, and the lab technician has purified it and increased the concentration to 11%. So what I'm trying to do with this experiment is I was trying to prove that the lactic acid that the technician has provided for me is at 11%. So we're just trying to verify if the technician was correct. There we go. Confirming your lab partner's work. So that is the whole purpose of what we're doing. So now we're doing our final step. We're tying it back to the beginning of the story and going, has this been done correctly? Cool. I think that's all I want to say for that. Now, in order for us to do that, we have done, obviously, all the practical component to it. And we have figured out a concentration for part C. So here's part C. And I hope I did the math one with you guys. Yes, I did. So when I did the math, when we did the math, we figured out the concentration of lactic acid was 0.0957 moles per liter. So that's going to be our answer that we're putting in from question 10, part C. So just copying that number down. 0.0957 moles per liter. There we go. All right, cool. So let me just pull that up here. So that's my summary of what we're doing. We're trying to work backwards to check the statements that we had originally. We have now gotten our value here. Now, something to keep in mind with these calculations is that this is only required for the excellence. So it says here, calculates the original concentration of lactic acid in the purified sour cream in grams per liter. So it's an excellence level requirement in what I'm doing right now. So if you're not aiming for excellence, then you don't have to worry about this. But I do suggest you guys give it a go because it's always worth giving it a go. All right, keep going. All right, so what we need to do is we need to work our way backwards to figure out if information is correct. So the first thing is we need to convert this back into the original solution that we had before we were diluting it. So we need to figure out what the dilution factor, and we get that information from above. So above, I said, when we made the solution, we had taken 25 mils of the purified sour cream, and we put it into a 250 volumetric flask. So what full dilution have I done? I did 25 and 250. I did a 10-fold dilution. So the first step that I need to do to start scaling things backwards is I need to times the concentration that I've had before by 10. So I would do 0.0957 moles per liter, and I would multiply it by 10 to get back to the original concentration. So if I multiply that by 10, I'm just moving it over one decimal place, so it's 0.957 moles per liter. And that is in the original solution before I diluted it. So 10-fold times by 10. If it was a 2-fold, I would times it by 2. If it was 4-fold, I would times it by 4. If it was 25-fold, then I would times it by 25. I'm just trying to get back to the original. That's what I'm saying. This is basically undoing what we did. All right, now we have to keep in mind that the data I collected is in moles per liter, but the concentration that I'm comparing it against is in grams per liter. So I need to convert from moles back into grams. So this step here is to convert from moles per liter to grams per liter. I have been given the molecular mass of my lactic acid, and they've reminded me what is the equation for N equals little m over big M. So right now my value is in N, and I want to solve for the little m because I want to go back into mass. So if I was to rearrange the equation, then I would have M equals N times big M, and that would be how I would convert it back. Are we okay so far? All right, so let's plug in our numbers. Our N value is actually our concentration. We'll just keep the whole thing in there. Moles per liter. And we're multiplying it by our grams per mole. What I notice when I do this is that the moles and the moles cancel out, but I'm then left with grams per liter, which is what I want. 90.08, yes. So 0.957 times 90.08. And what I get is that my final concentration is going to be 96. And I see, does it say that you need to have 3 sig figs in here? I'm just trying to check if it says 6 figs. Does not look like it is. Doesn't. I'm going to do it just in case. 86.2 grams per liter. And that's my final answer. So that's how much lactic acid I have. They're just going backwards, basically. A lot of forward and backwards in this assessment. Questions, concerns, comments? All right, keep going. There's a reason why you need that number, and that's for the later bits. All right. Huh? Okay. All right. So let me talk about the 3 different points. The first point here is justification of your procedure. This is optional because you could also get this in part A. Just trying to go grab a different color. So justification of your procedure is basically what you created in part A. You are allowed to revisit it in part D. So if you don't have it done in part A, you are allowed to also write about it in part D, but you don't need to if you've already got it in part A. For excellence. So this is an excellence point. This one here. All right. So justification for part A. Let me remind you what I was looking for part A. Go back. That's part 8. Okay. So most of you guys had gotten to this point. I have not seen many justify their results. So keep in mind, basically what I was looking for the excellence component of part A, and the same thing for part D if you haven't done it already. You only need to do it once. Okay? Do not write it twice. Save yourself the time. So what I was basically looking for is I wanted to understand why you selected the procedure that you did that was in here. Okay? There was several different things you can write about. You didn't need to write about all of them, but the more you write, the more evidence I have. I was basically probably looking for about 2. So first thing is explaining why you need to dilute your stock. So initially, when we did the first ratio check, we saw that if we used 1 ml of acid, it required 10 ml of base. If I was to scale this up for a titration and I used my smallest pipette possible, which is 10 ml, I would need 100 ml of base. And that is way, way too much. It also would not work for my burette because my burette only goes to 50. So first step you could state is I did this method because I needed to dilute my stock. Are we okay with that so far? This is all in Google Classroom, so I'm not going to write it down again. The second thing, or the second and third thing I should say, is you can justify then your range. So justify what your titrate volume is and why. So for the excellence, I was looking for a titrate volume between 10 and 25. 10 was your lower limit. You explain that 10 is your lower limit because of the 2% error in the equipment. Depending on what you've chosen, so in my case, I chose something that was a 10 ml titrate volume. If I had 0.2 is my error, so that means that my solution could be, when I'm reading it, be 0.2 above or 0.2 below, then I have a 2% error divided by 10 mils. It means that if I have 10 mils, I have 2% as my error. If I chose a larger titrate volume, say 20, I would have 0.2 divided by 20 times 100. I would have a 1% error in my results. So 10 was the lower limit because that's 2% error. If you chose a larger number, then you would decrease your error even more. Does that make sense to people? So that's your lower limit range and why it's the lower limit range. The upper limit range, it's scanned out of order, which is annoying, is why your upper limit is 25. The main reason for that is because the burette can only do 50 mils, and so I want to do at least 25 so I can hopefully do 2 titrations out of 1 burette filling. That's good for me because then it means less refilling the burette, then there's less likely to be error. So for example, when you refill it, you might forget your funnel, and that could affect your results. The other thing is we don't want to waste solution either. So that's why the upper limit was 25. So there's another thing you could write about and explain. The last thing you could write about is how many times can you repeat the experiment, because we know repeating the experiment is important to get our data and to identify outliers. And so you're thinking about the size of the stock you're making versus the aliquot you need to take of that dilution. So if I make a stock of 250 and I only need 25 mils of my the 250, then I could do the experiment 25 times before I run out of stock. So that's something that you can keep in mind, because the more data I have, the easier it is for me to identify outliers. The other thing is that we only want to dilute the solution once. So if I did the same thing and I only did 100 mils of my diluted solution, then I could only do the experiment 10 times. And let's say I needed to get more data, then I have to remake the stock of my dilution. And that is not ideal, because every time you dilute the stock, you're going to get slightly different numbers. So we want to use the original stock the whole time, the original diluted stock the whole time. So those are like the 4 reasons of why you selected your method. So tell me why you have to dilute, give me the upper and lower limits, why there's an upper and lower limit, and then talk about repeatability of your experiment. All right. Anything with a tick is deemed correct answers. You just have to explain why it's correct. All right. So that is part D for that first one. So basically it's just another chance to get part A. This one here is reflect on your accuracy, improving techniques. Explain how you ensured your results were valid and, accurate and valid by writing your methods and techniques. So this here goes all the way from achieve to excellence. For the achieved, I want you to describe accuracy, improving techniques. Now there is an S on there, so I would expect at least 2. Okay? With your accuracy improving techniques, there's lots that you guys can choose from. You could talk about getting to eye level. As your first example, you could talk about removing the burette. Removing funnel. You could talk about wiping your pipette. What else could you talk about? Just checking my notes. Rinsing your equipment. What else could you talk about? You could talk about the white piece of paper. What else could you talk about? Funnel, eye level. Let's see what else we got. You could write about, touching the pipette against the flask. Let's see what else. You could also talk about using the wash bottle just to move any extra acid into the flask. Trying to think what else. Eye level, remove funnel, drying your pipette, rinsing your equipment with what goes in it, the white piece of paper touching the pipette against the flask. I think that's it, actually. All right, so all those are examples of accuracy improving techniques. Like I said, I only need 2. So if you write more than 2, it just gives you more evidence. I would not suggest writing up all of them. So that one there describes the accuracy improving technique. So that just explains what you've done. That's why I've also included it in part C, so you guys can make notes of what you did while you were doing it, just so you can remember. I could also look there as evidence. Now, for the merit, you need to explain your accuracy improving technique. So why is it an accuracy improving technique? So for example, if I was going to eye level, the reason why I did that was to avoid parallelics error. Removing the funnel, I removed it because I wanted to make sure there were no extra droplets that fell down. Drying your pipette, you're removing any extra acid. Rinsing your equipment with what goes in it, you want to basically prevent, you want to clean it, but you also want to prevent dilution. Sorry guys, diluting. Samples. White piece of paper, that's so that way you can see the pale pink. Pushing the pipette against the flask, that's just to draw any extra acid. Then wash bottle to remove any droplets is just to make sure that all of your reactants are available to react in the flask. Are we okay with that so far? So that's basically give me a reason. Are we okay? All right. That one, like I said, does go up to excellence, and that is the justify how these two accuracy improving techniques ensure the quality of your primary data. So you're taking it one step further. So for example, this is all explaining why it's an accuracy improving technique, but it's not explaining the mechanisms to how it does that. So for example, avoiding parallax error, if I read it at the wrong angle, I'm going to underestimate the volume of my acid or base. So that is the how. And if you want, you can draw a little picture just to show what happens when you have a burette. And this is the bottom of the meniscus. And if your eyeball's up here looking down, it's going to be a different number than if your eyeball's down here looking up. That makes sense? I feel like I did that badly. All right, we're removing the funnel. There's no extra droplets of the base. So when you read it at one volume. And if a drop falls in afterwards, then you're going to misread it again. So it's all tying back to just misreading stuff. So that one there, no extra droplets. If it drops after reading, then you're going to have a higher volume. You'll miss out some of the base. Underestimate the amount of base you need. Drying your pipette, you're removing extra acid. If you don't do that, then you're going to have extra acid that needs to be neutralized. Rinsing the equipment with what goes in. You want to clean it without diluting the samples. If there's leftover water droplets, then it's going to dilute my acid or dilute my base. So the core of what you're trying to think about is how is it going to affect my final volumes? Yeah? So this one, and this one are all going to affect final volume. Rinsing the equipment causes dilution, so that means you're not going to have the right ratios. The white piece of paper is important so that you get the pale pink, so you get as close as possible to when the acid and the base equal each other. Sorry, it's all really squished in. I haven't thought this through very well. Say amount. Touching the pipette against the flask, again, draws the acid so you get the right volume. Wash bottle, again, making sure all your acid's there. So the base idea that you're thinking about when you're trying to explain the how is you're thinking about how is it going to change your results. So what you're thinking about here is how will a mistake at that step affect the results? Basically, it ties into wrong volume, and then when you use the amount equals. Let me start over. So most of these tie into wrong volume. And once you get the wrong volume, when you go and do the calculation of N equals C times V, the N amount will be wrong. And then all your calculations from then on is going to be affected. Hopefully that helps and makes sense. I'm not doing a terribly good job explaining it today. Questions, concerns, or comments at this point? Yeah. It's two. So you can pick any of these two to write up on. If you want to hedge your bets and you want to give yourself a buffer, you can write one more. Which I suggest you do, it's worth doing. So basically, tell me one of the techniques you used, what does it do, and then tie it back into how it's going to affect your results. The main thing is that it's just going to change your volume. And volume is very important because we're using that and the concentration to figure out about, because it's all part of the stoichiometry. All right, last thing you need to do, and this one here goes up to the excellence. So this second point here, you need to answer for the achieved, the merit, and the excellence. I'm going to put all three colors there, depending on what you're writing. All right. So part D, you do have to answer even if you're not aiming for the excellence, because this bullet point here is required for achieved and for merit as well. These two bullet points, the first one and the last one, and the calculations on that previous page are only required for excellence. So the last thing is you need to evaluate the results. So in this case, the lab partner said that it should be concentration of 110 grams per liter, but when you guys did the calculation, you found that it was actually lower. So we need to explain why is this lower than what my lab partner is saying. So we need to figure out what could have been the errors. So let me just pull up my notes. I'm trying to remember. All right. So two things that you can generically state for error. So why does your results not match the manufacturer or the lab partner's claim? So we have found that your results are 80, what was it, 86.2 grams per liter, but the data from the lab was saying that it should be 110 grams per liter. So we notice that the numbers don't match. We need to think about the reasons why. So generically speaking, there could have been a mistake in the purification process. Is one potential source. The second source of problems could be that the manufacturer has a problem with their quality control. So when they check the concentration, the concentration was not correct. So there should be some quality control process with all products just to make sure things are being made correctly, and something in what we call QC, quality control, failed. All right, so those are pretty generic ones, but the ones that are more specific, which is number 3, you have two choices depending on what has happened. If something is lower, or your results are lower than the original, it could be the result of you're testing an old sample, and the old sample could have degraded. In this case, the lactic acid has degraded. So that's just talking about whatever you're testing for. So if it's lower, it's probably that just degraded. If it is higher, then what has likely happened is that the manufacturer, that you have a really fresh sample. And so what has happened is the manufacturer knows that their chemical is going to degrade, so they make it a little bit more concentrated than it actually is. So by the time it gets onto the shelf, it is degraded to the concentration they state it's going to be. Does that make sense? So is basically very fresh. The manufacturer Sample is very fresh. The manufacturer has planned for the degradation of the chemical, so it's made it at a higher concentration. So we've unfortunately got that wrong because our sample's too fresh. So there's reasons why the number could be off. In this case, you have a lower concentration, so you are selecting the first option. It's degraded. So something to keep in mind with chemicals is that they are going to degrade over time. Some are better than others. But that's why you see things have a best before or a sell-by date. Just finish the notes. Good for you. All right, so just keep that in mind. So it's very likely that your concentration is going to be off, and we got to explain why. So mistake in the purification process, mistake in the quality control, or one of these two options. It's either an old sample, and because it's an old sample, our data shows the degraded results, so we need to get a fresher sample, or it's too high because we've got too fresh of a sample, and our manufacturer has planned for these things to degrade over time. Just one of those two. So depending on what your results are, you just pick the one that fits. So if the concentration that you get is higher than the concentration that is claimed, then you say, oh, it must have, if it's too high, then you say, oh, it's a really fresh sample. The manufacturer must have been accounting for degradation occurring by the time the item gets to the supermarket, and we have just gotten a too fresh sample. So yeah, choose one of these two. So you could say next time we should select a sample that has come from the supermarket instead of from the manufacturer directly, so that way it factors in the degradation. Or in this case, we picked a sample that's too old, and so I need to make sure that, we need to make sure that we buy a newer sample. All right? And that's the whole assessment. All right, let's pause the recording.